This technique of identifying the set like so with the span, I would like to generalize this as a statement, because you will be surprised how many times you will use, how often you will use this thing in the yellow book. How often in the yellow book this connection between the span and matrices is exploited. So I'm going to give a name to this statement. I'm going to call it span in Fn lemma. And here what it says. F, of course, it stands for my field. Does it say anywhere? So F, of course, stands for my field. So span, look at this. Span of vectors of M for Mary. Span of M vectors can be alternatively described as the collection of all vectors B, which are result of multiplication of the X vector from Fm by a fixed matrix A, where, look what's A and what's the A matrix is, where A, elements of Fn, be careful with the usage of the indices here, N and M, and A matrix, it's the matrix which is composed out of these vectors as columns. Here it is. You see, it's a matrix of size M times N rows, N for Nicholas, M columns, M for Mary. And that is the matrix with the coefficients from the F. F is a field. F might be either real numbers or complex numbers, or sometimes it may even be rational numbers. That is exactly what happened here. My M here is 3. My N here is 2. F here is the real numbers. Vectors A1, A2, A3, here they are in this setting. We're not going to prove this lemma. The idea of the proof is just right. It just explained right here. Basically, we proved that lemma in a special case, in a special case, but in the general case will look almost identical to the special case. But this sort of lemma, this sort of identification between the span and matrix multiplication and matrices, it's so ubiquitous in the yellow book, you can't live with this. That's why I single it out as a special statement, as a special lemma.